Are you seeing my screen?
Yes.
Okay, so today we begin our lecture 2, and before we commence, I would wish to respond to a question somebody asked yesterday about the prime numbers, and we had said that we would be showing how important prime numbers are as we progress. So yesterday, as we were doing it, we just came across one of the importance of prime numbers, but this is not very important to a computer scientist. The first importance that we discovered was through this theorem 4. The theorem 4 here talks about fundamental theorem of arithmetic. And from this point, we see that prime numbers are very important in the building blocks for the natural numbers. That any natural number can be written in terms of as a product of prime numbers. So that is one important importance of prime numbers, that we can represent all other numbers in terms of prime numbers. The other importance, we saw it, was this notion of factorization, prime factorization. And this becomes very important, especially in terms of security, when you go to things like cryptography and RSA, and especially when you're writing algorithms, you want that they are secure. So in RSA, for instance, and we shall see that when we reach there, you choose prime numbers. And the thing is, prime numbers, once you have two prime numbers, a product of those two prime numbers is not easy to be factored. Unlike if we were to use another number anybody can factor. So because of that complexity of the prime numbers, that is why they become very important in RSA. So prime numbers are very important, and as I said, we shall be seeing the importance of prime numbers as we progress. So those are just two. This issue of prime factorization will be very important in terms of RSA and security. And also another importance is here, at this point of testing prime numbers is also very important. We shall see that again later on, how the issue of prime numbers is also important, especially in security matters. Now, I think the other question we had answered, the other question, but it's this equation of prime numbers that I had said that we shall be seeing how important they are as we progress. Now, we had looked at division algorithm, just reminding us what we did yesterday. And the division algorithm is not an algorithm as such. That is just a name that it's given. Because what the division algorithm says is, for instance, if I have a number 6 and I'm dividing that by, let me say, 4. So I want to write this 6 in terms of 4, and I'm saying that 4 goes into 6 once, and the remainder is 2. So this is division algorithm. So it's not an algorithm as such, but that is the name it was given. But when you do that division, when you do that repeated division until you have a remainder of 0, then that what you've just done is the Euclidean algorithm. For instance, I've said 4 goes into 6 once and the remainder is 2. So when I now say, what about 2 into 4? And I say that 2 into 4 to be twice, and the remainder is 0. The remainder is 0. So what I've just done, using the division algorithm, what I've done is the Euclidean algorithm. So the Euclidean algorithm is this repeated division until you get the GCD. So the GCD now becomes the last non-zero remainder. This last non-zero remainder becomes the GCD of 6 and 4. So this is now the algorithm. The Euclidean is an algorithm, but division is not division algorithm. It's not an algorithm, but it's just a name it was given. So that is just a point I wanted to clarify there. And then when you use this Euclidean algorithm and reach here, then you write the GCD as a linear combination of the two numbers 6 and 4, as we were doing yesterday. That now is the extended Euclidean algorithm. Extended Euclidean algorithm. So that is also an algorithm. So those are the 2 points I want us to clarify. And that extended Euclidean algorithm is very important in today's lesson as we look at, because today we're supposed to look at congruences and linear congruences as we solve those modular arithmetic. So let me just now go to where we're supposed to begin from today. We had looked at the number spaces. So today we're supposed to look at modular arithmetic. And I began by saying that this one has a lot of applications in computer science. For instance, when we'll be looking at pseudo-random numbers and hashing functions and also cryptology, this modular arithmetic becomes very important with a lot of applications there. So what is the definition? I've said let m be a positive integer. We say that the integers a and b are congruent. And this is how we write it. So we say that a and b are congruent. So we shall be using this symbol here to mean they're congruent. A and b are congruent. So this is a symbol we'll be using. But when do we say that they are congruent? We say they are congruent mod m. They are congruent modular m or mod m if m can divide the difference. If m can divide the difference of a and b, then we say that a and b are congruent mod m. That is one way of looking at that definition, looking at congruence. That's one way. But there's another definition I'll give you. These two definitions, we'll be using them as we progress. So that is a definition. When do we say that a and b are congruent? I've said we say they are congruent if mod m, if that m can divide the difference between those two. But if m cannot divide, then we say they're not congruent. And this is how we write it. That m cannot divide. If m cannot divide a minus b, then a is not congruent to b mod m. Just a small example here. The question is 10 congruent to 4 mod 3? So I want to check that. I just check the difference and see if 3 can divide that difference. If 3 can divide the difference between 10 and 4, that difference is 6. And of course, 3 can divide 6. And so it's true that 10 is congruent to 4 mod 3. The reason is given here, that because 3 can divide this difference. What about 10 being congruent to 1? I just again subtract. So 10 is congruent to 1 mod 3 because I can see that 3 can divide the difference between 10 and 1, which is 9. So 3 can divide 9. So it's true. But the last example there, Again, I just get the difference between 22 and 4, and that difference is 18. And I can see that 3 cannot, no, 5 cannot divide this difference, and therefore 22 is not congruent to 4 mod 5. So this is like a base. This is like base of 3, base of 3, base of 3, base of 5, and so on. So let's take it as a base for now. It's like a base. So we're saying if a number A to be congruent to B in the base of M, so we are writing mod M, then it will mean that M must divide the difference between these two numbers. That is the definition. That's the first definition of congruence. I've said something here. I've said that if I'm given 3 numbers, A, B, and M greater than 0, then you can say that B is congruent to M mod M. If B equals to M times T, where T is an integer. Where T is an integer, so T is a number in this range. The range, these are the integers. -2, -1, 0, 1, 2, and so on. So T can be any of these numbers. So you're saying that B to be congruent to A, then B should be the same as A plus M. Remember, this M is our base. We are doing it mod M. So this M is our base. So this base times any integer. And I just want to show this definition by use of this example. That definition, I want to use that definition to do this example. And the example says, which numbers are congruent to 3 mod 7? So it's the same as this. This question is the same as this. Find X which is congruent to 3 mod 7. So find all numbers which are congruent to 3 mod 7. So we've said, and look at this. And again, another definition. Let's just give you another definition of congruence, although it's below this page. Another definition, the number here. This number here is the remainder when you divide by 7. So what one is saying, for instance, is that my internet is unstable. I don't know if they can hear me.
Yes.
Can you hear me? Pop up that the internet is unstable. Now, what this is saying, if I was to give another definition of congruence, this one is saying what numbers, when divided by 7, the remainder will be 3. What numbers when divided by 7? So what is X? This X on division by 7 gives you a quotient. The quotient is that, and there's a remainder. And the remainder here is 3. And this is where you find this. This definition is coming from this. This is coming from this, because if I had this to get X, if I have T as the quotient and 3 the remainder, get X, I would take 7 times the quotient and then plus the remainder. So that is another definition of congruence. And that is where, from this reasoning, that is where we come up with this. We come up with this from this reasoning that when you are given this, it means find a number which, when divided by 7, the remainder will be 3. So those numbers are many. Those numbers are So because we are choosing it from the integers which are infinite. So we're choosing it to be from integers. So whichever you choose, you get an x. For instance, if I was to choose to be 0, then my x will be 7 times 0 plus 3, which will be 3. If I choose to be 1, then I would have x to be 7 times 1 plus 3, which is 10. If I choose to be -4, for instance, then 7 times -4 would be -28. And plus 3, that would be -25. And so that is how I got all these values. That's how I got all those values. So you can see this one, this -25, I chose t to be -4. So when t is -4, I go to -25. When t is -3, so I have -3 times 7, which is -21. Then add 3, and that gives you -18. So all these numbers are congruent to 3 mod 7. All these numbers are congruent to 3 mod 7. So just looking at what numbers, when divided by 7,
Mwalimu tumepoteza.
So what Mwalimu was telling us is going to usher in logarithmic equations, and they're replicable in cryptography. When it comes to RSA, so RSA is basically the cipher you use when you're creating, the process you use when you're creating a cipher. So what you have to keep in mind is the whole process is supposed to be easy. Like the product of n, which is p and q, is supposed to be easy, but the reverse is supposed to be hard, because we know that the blockchain bytes are 256, and the value in itself intrinsically is a large figure. Say n is the product of p equals to p times q, where p is 256 bytes, where the log of that p is about, I'm not, the value is not accurate, I don't have the accurate value, but it's about into the billions. So before somebody guesses what p could be multiplied by q, and q could be any value. Now q is the number of words that you want to convert into a cipher. So you see, it's going to be hard for someone to guess that. There's something called cryptanalysis, cryptanalysis, where these are basically the hackers of blockchain. They try to find vulnerabilities. That is when a scare, something was hacked, a certain ecosystem was hacked. So basically, that is what they do. And we have really, really smart people who make sure that that's not possible. That's why you hear like Ethereum has a bounty for people who can identify vulnerabilities. So Molimu is back, so that is what we shall be doing when it comes to application. And yes, it's very interesting actually. I hope to see you guys then. Mr. Secretary is back. Molimu, can you hear us? So just keep that in mind. Keep in mind that this is the basics. It's supposed to usher us into logarithmic functions where the product of n is p and q, and the reverse of it is hard. That's the whole point of cryptography. And we will get there. So do your best with the basics. And then when it comes to application, it's going to be much, much better. I promise it gets better. There's a light at the end of the tunnel. So yeah, I'm just gonna leave it there.
Can you see my screen?
Yes.
Yes.
It's okay, it's okay. I have some challenge with the internet. Let me just some minutes. Now, so we're looking at I was giving this definition. And the definition is I had already talked about it, where can you hear me?
Yes.
It's okay, thank you. Now, so I had said that if I'm given M mod M, then what that means is that I find the remainder when A is divided by M. This question, what is 14 mod 5? So the question is, if 5 were to go into 14, what will be the remainder? So you find that the remainder will be 4. If 10 were to go into 139, remainder will be 9. If 5 were to go into negative 14, and you know how to divide 5 into negative 14, 5 will go there how many times? Negative 3 times. And this gives you negative 15. When you subtract that, the answer will be 1 positive. So the remainder is always positive here. So 5 will go in negative 14, negative 3 times. So that when you subtract, then the remainder, that is another definition of congruence. That what is the remainder when you divide by that mod. Now, so there's other questions, the other examples here. I want to do example F. Example F, just using the properties. And you see, if I'm given 17 plus 23, and I'm asked to find the remainder when divided by 5, what I then do, I do for the first one, the remainder divided by 5, the remainder there will be 2. And then for this second one, divided by 5, and the remainder will be 3. So that means the sum, this sum, divided by 5, the remainder will be 5 mod 5. So we're asking if 5 were to go into 5, what's the remainder? So long as this number is equal to this or more, you have to reduce it. If it equals to this, the mod, or it's more than the mod, you have to reduce it. So 5 goes into 5 once and the remainder is 0. That means the answer to this question is 0. So you do for the first one and then you do for the second one. The same thing with this, mod 4. So 4 into here, into 18, to go there 4 times. Because of 16, the remainder will be 2. And then 4 into 23, because of 5, the remainder will be 3. So what I then have is 3 plus 2 mod 4. But this number here, 5, is greater than 4. So again, I'll use it, find the remainder. If 4 are to go into that number, and the remainder will be 1 mod 4. Now, the same thing happens with the product. The same thing happens with the product. You ask yourself, if 5 are to go into 19, what will be the remainder? So 5 goes there 3 times. Because of 15, the remainder is 4. And then again, 5 into this, what will be the remainder? And again, the remainder I found it to be 3. And then mod 5. When you do this, you get 12, which is bigger than 5. So again, we have to ask ourselves, if 5 were to go there, what will be the remainder? And the remainder there is 2. So that becomes the answer to this question. So let me just clear here. So once you realize that we are just finding the remainder, it becomes very easy. The same thing happens to this. The same thing happens to this. I would ask myself, if 4 were to go into 11, what would be the remainder? So 4 goes there, you get 8. So the remainder will be 3. So that means, in fact, 11 squared is just the same as 3 squared. We are doing it mod 4. What about 13? 4 into 13, because of 12, the remainder will be 1. So that is 13 square, just the same as 1 square mod 4. But what we are doing was that 11 square times 13 square. So which is the same as 3 square times 1 square mod 4. And so this is 9 times 1 mod 4. The product here is 9, which is bigger than 4. So you have to reduce it again. If 4 were to go into 9, the remainder will be 1. So that is how I get this result. Now, so let's look at this other one. So the question is, what's the remainder if 19 were to divide this number? If 19 were to divide this number, what would be the remainder? A calculator cannot do this, but you can come up with a program to do it. We can also do it here. Now, so what we do, we first of all reduce this number, just the same way we reduce this 11. We said the 11 here, this example, 11, if 4 were to go there, 11 mod 4, we said it will be the same as 3 mod 4. So we then said that if 11 were raised to any number, it will be the same as this 3 raised to that same number. So that is what we do here. So we ask ourselves, if 19 were to go into that 5, what would be the remainder? So we just, and you find that, what would be the remainder there? 19 from 35. This gives you what? 6. And this gives you it's supposed to be 16. Is it the remainder? When 19 goes to 35. Hello? using a calculator, you get 16.
Yeah.
Yeah, you get 16. So I think what I wrote here was not, I wrote 1, or maybe it was 16, but because of typing, the 6 could not come out. But let's just do this question now. So if 19 were to go into 35, you've told me that this would be the same as 16. The remainder will be 16. So if I raise this 19 to 20, 24, it will be the same as this raised to 20, 24. So there are very many ways of doing this question, but I want to show you the one of squares. I want to show you the one of squares. Although I intended to do, because I've done the one of squares below. The one I wanted to do, I thought it was to give me a remainder of 1. So that would have made it. I don't know why I thought it was a 1 when it's a 16. I don't intend to do the one of squares. I've given it another name below this slide. Let me do this. 14 into 27, you find the remainder. So the remainder, when you are doing this question using this modular arithmetic, you want to have the remainder to be as small as possible, either 1 or negative 1. So you want it to be either positive 1 or negative 1. So if 14 were to go into 27, the remainder is what? 13. But 13 is the same as negative 1 more 14. 13 is the same as negative 1. So we have just subtracted 14 from negative 1. No, 14 from 13. When you subtract from 14 from 13, you have this. So these two numbers are congruent. Let me just show you. If 14 were to go into negative 1, what will be the remainder? If it were to go into negative 1, 14 goes in negative 1 times. And then negative 1 times this is negative 14. When you subtract this, you get 13. So these two numbers are equal. Negative 1 and 13 are equal numbers. They are congruent. So that's why I said 13 is the same as negative 1 mod 14, because if 14 were to go into negative 1, the remainder will be 13. Now, so the trick with this approach is that you have to make your remainder as small as possible, either positive 1 or negative 1. So we've seen that 27 reduced mod 14 is the same as negative 1 mod 14. So that means if I was to raise 27 to any number, the same as raising this negative 1 to that number. And since there's a negative, it's always good to put a bracket here. So this is negative 1 raised to 1001 mod 14. Negative 1 raised to an odd number, the answer will be negative 1. And the negative 1 is just the same as 13 because we have converted our answer to be positive. The remainder is supposed to be positive. That's why I have this as the remainder. That if 14 were to go into this number was positive. If 14 were to go into this number, the remainder will be 13. The remainder will be 13. So you can see the steps we've used. the steps we've used, one, we've reduced this number, mod 14. It was 13. So then I reduce it again so that I have either +1 or -1, if it's possible to make it +1 or -1. If it's not possible, like in this case of example 25, then there's another way I'll show you after this. But if it's possible, 1 or -1, then it's always easy to do that. Let's look at another example. Or before that example, now I now want to show you the method I was talking about, which we call the fast powering algorithm. And the fast powering algorithm is also known as the exponential squaring algorithm. And this one, you use it to get powers of numbers. If you have a number to the power of very big power, then you use this method, like the example that I skipped above. Now, this method, when combined with the other Fermat's little theorem and the Euler theorem, which we shall also look at, they make your finding of the powers very easy. If you have a number that is raised to a very big power, then you combine this fast powering algorithm together with the Fermat's little theorem and the Euler theorem, and you get that product or the remainder very fast. So it's a very good method, especially when we shall be getting universes of numbers, and you'll be having a number that is raised to a very big power, and you're asked to find the inverse. If you have a number that is raised to, for example, 2 raised to a very big power, and then asked to find the inverse mod 17. And then we look at what Fermat's little theorem says, or what the Euler theorem says, and then use this fast powering algorithm, combine, and then get the inverse very fast. So let's look at an example where I'm using the fast powering algorithm. Now, what does it say just before that? This algorithm works as follows. That's what I've said. It works as follows. To find n raised to k, we do the following. If you're given n raised to k and you're asked to find what the value is, the first thing you do, you get n, and then you square it. You square this n, and then you square this number, n raised to 4, and then you square this number, you get n raised to 8, then you square this one, you get n raised to 16, and so on. So after you've done that, you choose from this sequence which numbers would give you this product, will give you this power. So you're choosing, for instance, supposing this n is 36, this k is 36, supposing it's n raised to 36. And using the law of indices, you're thinking from this, what you have here, how do you get 36 from this, what you have? I can say I can get 36 by 16 plus maybe 16. That gives me 32. And I'm left with 4, then plus 4. So I have this 4 here. So that is what we'll be doing. So I'm given, for instance, n raised to 6. I take n. This is n raised to 1. Then square it. Get n square. Square it again. Square this one. Get n raised to 4, and so on. And then choose from that sequence the numbers you can add to get what you have here. And you, of course, will be using the laws of indices, which we already know. So let's try to go to an example. I have 2 raised to 71. And the question is, What is 2 raised to 71 mod 9? We have already said this means what is the remainder? We've already said it means what's the remainder when this number is divided by 9. So we use the first powering algorithm. I just take this 2 raised to 1, then it 2 raised to 2. So let me just arrange them. Let me arrange them and so that I get the values. 2 raised to 1 is 2. And then raise this one to 2, square this, I get 4. And then square this, that is 2 raised to 4. And we are doing it mod 9. So this would be 16. 16 mod 9. So what remains when 9 goes into 16 is 7. That's what we write. And then square this. So to square this, I don't need to square 16. I square this, 7. Because 2 raised to 4 is 7. That is what I square. And I get 49. Mod 9. So I'm asking myself, if 9 were to go into this, what do I get? What do you get? If 9 goes into 49, you'll get, it goes there 5 times because of 45. And the remainder is 4. That's what I write. Then square this one again, square this, get 2 raised to 16, which is 4 squared. 4 squared is 16, mod 9, because we are doing it mod 9. The remainder is 7. Then again square this, and get 4. Square this and get 4. So somebody will be asking, how many times are you going to square? And again, I'll answer that question in a short while. How many times are you going to square? But there's no problem. We're just squaring until the number here moves as close as possible to this number. Because what we want is 71. You realize that if we were to square this one again, we'd get a number which is beyond, and that would be 128. 128 is beyond 71. So that means we cannot go up to that point. We stop at this point. We stop at that point. So this is the first powering algorithm. And then after that, I want 2 raised to 71. And I'm using indices, law of indices. What is 71? 71 is 64. This 64, I have it. Then I'm checking from this list what I have. What am I left with? I'm left with the 64 from 71. I'm left with the what? 71 minus 64. I'm left with the 8. Power 8. Power 8 is, oh, power 8 is here. No, it's not 8. This is 7. The difference there is 7. It's not 8. Yes. The difference is 7. So power 7 is not here. So the one that is closest and less than 7 is 4. So when I reduce 4 from 7, I'm left with 3. Power 3 is not here. The one that is closest is 2. So again, I'm left with 1. So this is what I have. So the law of indices then says that if I have this, is the same as 2 raised to 64 times 2 raised to 4 times 2 raised to 2 times 2 raised to 1. But the 2 raised to 64, we have it as 7. And 2 raised to 4, we have it as what? As 7 again. And 2 raised to 2, we have it as 4. And then 2 raised to 1 is 2. I'm doing it mod 9 Now, you can decide to multiply all these numbers and then divide by 9 and get the remainder. Although I don't want to use a calculator because I don't have a calculator here. What I know is that this 7 is the same as -2 mod 9. 7 is the same as -2 mod 9. I just subtracted 9 from 7 and I got -2. And this 7 also is -2. And let me just, this is a small number, I can deal with that. This is also a small number, I can deal with that. But the bigger numbers, because I don't want to use a calculator, I can reduce. So -2 times -2 is 4. 4 times 4 is 16. 16 mod 9, from this point to this point, 16 mod 9, that is 7. Is it? 16 mod 9. The remainder when 9 goes there is 7. Then times this 2. This is 14. It's a small number to deal with. 14 mod 9 is 5. If 9 were to go into 14. But again, if you like what I've done here, you can still do that. This 7, you can still reduce it to -2. And then multiply by this 2. Reduce this -2, multiply by this 2. What you have here is -4 mod 9. I want this answer to be positive because I was dealing with a positive number. So I asked myself, if 9 were to go here, what would be the remainder? So I just do that by adding this 9 plus this -4, and I get 5. Because I know if 9 were to go into -4, to go there -1 times, so that -1 times this would be -9. And when you subtract this, you get 5. So that's what I did here. So this is the first powering algorithm. Now, just a small explanation here on the first powering algorithm. And let me just again remind us what we did. We had 2 raised to 71. And we said we will take 2, then square it, and then continue squaring. Continue squaring. So this I, the I here are the numbers 0, 1, 2, 3, and so on. So for this case, it's 0, 1, 2, 3, 4, 5, 6, 7. We did 7 times. So this went up to 6. Went up to 6. So I was 0, 1, 2, 3, up to 6. That's what we did. So what this means, therefore, when I is 0, what you have is 2 raised to 2 raised to 0. 2 raised to 0, any number raised to 0. The answer is 1. So that means when I is 0, I get 2 raised to 1. And that's what I have here. That's what I have. When I is 0. When I is 1, using this formula, I have 2 raised to 2 raised to 1. So 2 raised to 1 is just 2. And so I have 2 raised to 2. And that's what I have here. When I is 2, I get 2 raised to 2, then raised to I is 2. So this is 2 raised to 4. That's what I have here. So I'm just squaring these numbers. I'm just squaring. Then what about when I is 3? When I is 3, I have 2 raised to 2, then raised to I. This is the same as 2 raised to, this part is 8. This part is 8. So that's 2 raised to 8, and so on. So that is the explanation I wanted to give, that I'll now from now hence, I'll be using this. I'll be using this to do that. And so the question here is this: how did we know that we are going to square 7 times? How did we know? Because I squared 7 times. I had already said that one will just, if you don't want the reasoning below here, you would just square until this number here is less than or equal to this, but it should not be greater than the power you want. But now that is not what I did. What I did was I took this power and then converted it to, you see, this is a decimal number. I then converted to binary. I converted to binary the way we were doing yesterday. So when you convert 71 to binary, this is the number you get. When you convert 71 to binary, this is the number you get. This number has how many digits? 1, 2, 3, 4, 5, 6, 7 digits. It has 7 digits. So what that then means is that I'll square 2 7 times. I'll square 7 times. That's what I did. This is the first time, second time, third, fourth, fifth, sixth, then 7. So this method becomes very important, especially when you're dealing with a very big power. For instance, you're dealing with something like this. And you see, you cannot just start squaring blindly. So what I then do, if I'm dealing with this, I would convert this number, first of all, to binary, so that I know how many times am I going to square this. So that as I begin squaring, I know what I'm doing. I know where I'm supposed to go. So I'll just take an example to emphasize that point. I have this example: compute 3 raised to 265 mod 17. So this number is a bit big. This one is smaller. If you want, you can just begin 3 raised to 1, get what that one is. Then 3 raised to 2, get what that one is. Then 3 raised to 4, get what that one is. Then go up to when you're just approaching this number, or when you reach it, and then stop. But that is not what I want to do. That's not what I want to do. What I want to do, I want to begin knowing where I'm going to. So I want to convert this number, this power, to binary, the way we were doing yesterday. When I convert it to binary, this is the number I get in binary. So this number has 1, 2, 3, 4, 5, 6, 7, 8, 9 digits. So that means 0, 1, 2, up to 8. These are 9 digits. And so this is my I. This is my I. So I'll take 2. Oh, no, it was 3. It was 3 raised to 2, then raised to I, where I ranges from 0 to 8. And this is exactly what I did. This is what I was doing. So let me just let's start now, go through the what. We now know that we're supposed to do it 9 times. So when I is 0, this is what I have: 3 raised to 2 raised to I. So when I is 0, the fact that I'm getting is 3 raised to 1, which is just 3, which is just 3. So I is going from 0 to 8. Now, when I is 1, I have 3 raised to 2, then raised to 1, which is just 3 raised to 2. And remember, I'm doing it mod 17. So whenever it goes beyond 17, or whenever it comes to 17, I have to divide by 17 and write the remainder. This one is less than 17, so it's just 9. Okay. Of course, you know that I'm now squaring this. I'm squaring this to get the next thing. Because I squared this to get 9, so I'm just squaring this to get the next thing, which is 81, of course, to be 81. 81 is bigger than 17. So I asked myself, if 17 were to go here, what would be the remainder? Use your calculator and see that you get 13. That's what I got. And then again, just square this if you want. And if you don't want, you can also use this. You can use this one. It's now 3 raised to 2 and raised to 3.
Mwalimu, I have a question.
So yes.
All right. So when you're trying to find binary, you have to use to the powers of 2.
Okay. Let me just explain. This 2 means square. It does not mean binary. It means we are squaring. We are squaring these numbers repeatedly. The binary is only assisting us to find out how many times are we going to square. How many times are we going to square? So the binary, the role of the binary only reaches here to just give us I is beginning from 0 to what number. But this 2 is a square. So we are squaring. That is what this fast powering algorithm says. Fast powering algorithm says you square the first number, then square it to get the second number, then square the result to get the third number, square the third number to get the fourth number, square the fourth number to get the fifth, square the fifth, and so on. Because
Okay.
that is what the 2 means. We are
Understood.
squaring and
Yeah. Because I was wondering why are we not cubing it or any other number. So fast power algorithm requires that we use square.
Yes, you square the numbers.
Okay.
Yes, exactly. Now, so in fact, without the binary, we would just have squared. We would have taken 3, then raised to 1 to get the first number, then take this first number and square it to get the second number, which is 9. Then again square this second number, to get 3 raised to 4, which is 9 square mod 17. And this is 81 mod 17. So if 17 were to go into 81, what is the remainder? The remainder will be 13. And then square, this was the first number. This is the second number. This is the third number. Square this third number. Square this third number. When you square this, you get 3 raised to 8. And then square the result. The result was 13. Square this 13 and get 169. Reduce it, mod 17. Ask your calculator, how many times, if 17 would go here, what would be the remainder? We'll get the remainder to be 16. Then square this recent result. When you square the left side here, it will be 16 here, the power. And then the result was 16. Square this 16 again, and then reduce it to mod 17. You'll get your result to be 1. Once you get 1, subsequent squaring does not change it. So because if I was to square now this current number, I'll get 3 raised to 32 and square the 1, I'll just remain with 1. And again, so that is when, once you get 1, the results remain 1, 1, 1, and so on. Now, whenever you get a 1, that makes your work very easy now. When you make 1, you make your work, when you get it, your work becomes easier. Because now we know that for us to get the result, we don't need, if we would not have gotten 1, we would have checked through this and tried to add. Because what we wanted to get was, what was it? Was 3 raised to what? was 3 raised to 71. No, 3 raised to something, it was something big. Well, let me just go back. It was 265, yes. It was 3 raised to 265. You know, the one here has made our work easier. Otherwise, we would have said that this is the same as 3 raised to 256. And then subtract this 256 from this, got the remainder to be 9. Yes, 9. And then we check the power of 9 here and found that the nearest is 8. And then plus 1, which we have here. So that will, you see, this is a lot of work. This is a lot of work because I'm now I'm multiplying this, which is 1 here. And then times the one that has power of 8, which is 16. And then times the one of power of 1, which is 3. And this is a lot of work. But although it will give us the same result, let me see. Yeah, it will give us the same result, but it's a lot of work. Let me just see if that I've picked. Let me see that I've picked the right thing. It's okay, it's okay. This is 48, is it? This is 48. Now, if there were bigger numbers, then it would have been a lot of work. So this one is not a lot of work because we are dealing with smaller numbers. But if we are dealing with bigger numbers, and I got a 1 in my table somewhere, it becomes easier. Just go to where the 1 is. Where the 1 is here. And then from that point, I can see that 3 raised to 16 is 1. But what I want is 3 raised to 265. Let me just confirm if that is what we want from the question. The question wanted us to get 3 raised to what? Yes, 265. Now, once I get this, that there's something that when I raise to 3 to something, I get a 1, becomes easier. So I just say, I've already found that 3 raised to 16 is 1. But we require 3 raised to 265. So what is the relationship between these two powers? 16 and 265. What is the relationship? So we use the division algorithm. What is 265 in terms of 16? So you're asking yourself, if 16 were to go there, what would be the remainder? You just use your calculator and tell me what you get. If 16 were to go here, go there how many times? And what is the remainder? That is our division algorithm that we learned. So what you get? If 16 were going to 265, how many times will it go there? And what will be the remainder? So you can use your calculator, even the phone, you can do that. So I just take 265. I take, then just, that is 265 divided by 16. No, 17. It is 17, not 16, actually. It is mod 17. We are doing mod 17. Oh, no. No, we are relating these powers. We are relating these powers. We are relating these powers. We want to see the relationship between the powers. So we are divided by 16. 16 goes there 16 times. Goes there 16 times into 265. Let me find what the remainder is. The remainder is 9. That's what you get. Now, so we have this. We have 3 raised to 16 is 1. But we want 3 raised to 265. So what is 2 raised to 3? No, 2 raised to 265. Just erase that. So once we've used this division algorithm, 3 raised to 265 is then the same as 3 raised to this. Because this is our 265. This is our 265. 16 times 16 plus 9. This is our 265. Now, this is same as 3 raised to 16 when I use the law of indices times 3 raised to 9. But this first part is 3 raised to 16, then raise it to 16 times 3 raised to 9. This first part, we know what it is. 3 raised to 16 is 1. So this is the same as 1 raised to 16 times 3 raised to 9, which just gives us the result as 3 raised to 9. So I come back here and find out what 3 raised to 9 is. What I have is 3 raised to 8. So 3 raised to 9, the same as 3 raised to 8 plus 1, which is 3 raised to 8 times 3 raised to 1. But 3 raised to 8 is 16. And 3 raised to 1 is 3. So I have 16 times 3 mod 17. This is 48 mod 17. So if 17 were to go there, what would be the remainder? In fact, 17 times 3, no, times 2 is 34. So 34 from here, you get 14 as the remainder. So the answer to this question, therefore, is 14. The answer is 14. But still, I would have done it this way. I would have done it at this point, instead of multiplying this and then messing up, I would have done it 16 mod 17 is -1. Then times this 3, I get -3 mod 17. And then what is this? Just add 17 plus this and get 14. Is that okay? So that's how you do that. So when you get that there's a power that gives you 1, that simplifies your work a lot. That makes your work easier. So let's look at another example. So the continuation of that result was here. The continuation is here. So that's how I done up to the end. Now let's do this. This time I've decided not to use, to change the base to the power. I've decided not to change the power to binary. Just decided to try and see, try and multiply, try and square, just try and square and see what I get. So I just squared 12 raised to 1, I got this. Then square the first result, get, that is 12 times 12. And we are doing it mod 17. Mod 17, here we have calculator, this 144, divided by 17 and get the remainder. If you don't have a calculator, as 12 is the same as -5, and this 12 again is the same as -5 mod 17. That is, I'm just subtracting this from that, by getting -5, -5. When you multiply these two, get 25 mod 17. And then I ask myself, if 17 were to go here, what would be the remainder? And that remainder is 8. Then again square this, 12 raised to 4, 8 square, 64, mod 17. If 17 were to go here, the remainder will be 13. That we are using powering algorithm. Say square the next number, square to get the next number. So again, let me square this. I get it 12 raised to 8. And 13 times 13 will be 169. Then 169 mod 17. If I don't want to do that, I know it's 13 times 13 mod 17. And I know that this will be 4 negative. And this again will be 4 negative mod 17. And I know that when I multiply this, I get 16. And again, square this. That is 16 times 16. I'm doing it mod 17. And I know this is very close to 17. This is negative 1 times negative 1 mod 17. And this gives me 1. Once I reach here, my work has been simplified. I don't need to continue squaring. I stop at that point and then find out what the result is. I have reached at this point. I've reached at this point. So I go back to the question that I have been given and get the relationship between the powers using division algorithm. So by division algorithm, 2024 in terms of this power. So I'm asking myself, just a minute. Now, so by division algorithm, I'm asking myself, if 16 were to go into this number, how many times would 16 go there? And what would be the remainder? So with my calculator again, I divide 16 into 2024. 2024 divided by 16. Calculator says it goes there 126 times. And what is the remainder? So I just subtract this 16 times 126. The remainder is 8. So then, what is 12 raised to 2024? This is same as 12 raised to this. This is 2024. This power here, this is our new power. So it's 10 times 126 plus 8. This is 12 raised to 16 times 126 times 12 raised to 8. But this first part gives us 1. Because the first part there is 12 raised to 16, and then raise it to 126. And then this other part is 12 raised to 8. Whatever is inside the bracket here was 1. So what we then get here is 1 raised to 126 times 12 raised to 8. So what gives this gives us 12 raised to 8. But 12 raised to 8, we have it. Is 16. 12 raised to 8 is 16. And so that becomes our remainder when you divide 17 into this number. So the same method, you can use it to do this example 30. The same method. And example 30, or let me just do it. Example 30 is like the one I had skipped earlier. This one, first of all, you reduce this, 24. 11 into 24, the remainder will be what? So 11 into 24, that is, no, 11 24, you get 22. Goes there twice, so 22, the remainder will be 2. So somebody giving you 24 raised to 64 or 62, this is same as 2 raised to 62 mod 11. So you reduce, whenever this is bigger than the mod, you reduce it first of all. Then you, after reducing, you now do what you've been doing. You now do what you've been doing. So you, first of all, you take 2 raised to 1, which is 2. Then what about 2 raised to 2? Would be 4. Remember, we are doing it mod 11. And then it's square it again. 2 raised to, and when you get to know this thing, it doesn't mean every time you must square. You can even get cube. You can even cube. Let me now show you that I can even cube here. It was square. If I cube it, what do I get? You see, if you cube, what you get here is just 2 square times 2. But the 2 square is 4. And 2 is here. So this is 4 times 2, which is 8. You can even now say 2 raised to 4. There's no problem. 2 raised to 4 is the same as this. This one is square. Or it's 2 raised to 3 times 2. But 2 raised to 3 is 8. Then times 2 is 16. Doing it mod 11, that gives you 5. You can even find 2 raised to 5 now, which is 2 raised to 4 times 2. 2 raised to 4 times 2. But 2 raised to 4 is 5. Then times 2, and this is negative 1. Mod 11. It's negative 1. You can call it 10 or negative 1. I've chosen negative 1 because I want to make my work easier here. I've chosen negative 1 because I want to make my work easier. Because I know that 10 and negative 1, they're congruent. Mod 11, they give us the same remainder. Now, once I get this negative 1, then my work has become easier now because I've seen that 2 raised to 5 is negative 1. What I want is 2 raised to 62. What I want is 2 raised to 62. This one. So I have to write 62 in terms of 5 using division algorithm. Yes, the remainder will be 2. Now, so that means therefore 2 raised to 62 is the same as 2 raised to, I think my internet has a problem. But you can still hear me, is that okay? Because I want to just do this example, then the next one. You can still hear me.
Yes, we can hear you.
Is okay? So this is 2 raised to 5 times 12 plus 2. And this is 2 raised to 5 times 12 times 12. There's a dot there. And then times 2 raised to 2. But this one is negative. This one is what? This is 2 raised to negative 5. No. Raised to 5. And then raise it to 12. And then 2 raised to 2. Just create some space. So, but we know what 2 raised to 2 raised to 5 is. It was negative 1. This negative 1 raised to 12. Then times 2 raised to 2. Negative 1 raised to an even number, the answer will be positive 1. Then times 4. This is 4. In fact, this is the answer to that question. 4 mod 11. 4 mod 11 becomes the answer that this question. Now, so I'll not do question 31, but I just explain what you're supposed to do. First of all, do this mod 17, get the answer. Then you do this again, the way we've been doing above, mod 17, get the answer. And then add the two answers. So you do this one first, mod 17, get the answer. Then do this one, get the answer. Since the answer is, there is a summation sign here, you sum the two answers. If this sign would have been multiplication, you would have multiplied the two answers. So you do the first one, you do the second one, and then you multiply the two answers. But now this one is plus, so you have to add the two answers. That's why I say we calculate this one first, then calculate this one separately, using the above strategy, then add the two answers. So of course I've done it here, but you can try and see whether you get the same result. I've said here is longer for bigger powers. And because it's longer, sometimes we now combine it, as I had said, with the Fermat's little theorem or by Euler theorem to make it easier. So those ones are covered in section 11 and section 14, respectively. There's this theorem which I will not prove. What I've just said that every number is congruent to itself. That is what part S says, that A is congruent to A mod M. And you know what that, to prove that is very easy. Because we know, we asking ourselves, does M divide the difference? Does M divide the difference is the question. The difference is 0. So M would divide that difference. And so you'll have proved, if you just do that, you'll have proved this first part. That first part says that. The second part also is very easy to prove. They're saying that if A is congruent to B, then B is congruent to A mod M. So it's just easy. You ask yourself, what does this one mean? What does this one mean? This first part means that M divides the difference. What happens if I was to multiply this by negative? If I was to multiply this part by negative, I would have negative into A minus B side. What I then get is B negative A. What I get is B negative A. So M divides B negative A. And this is how we write it. This is how we write it. That B is congruent to M mod M. This is how we write this. So that is what that says. If A is congruent to B mod M, then B is congruent to M mod M. This is how you prove it. By just multiplying by a negative. Now, so I think we can stop there so that when we meet next, we look at these integers, these rings. And then from there, we are now ready to look at inverses. I stop there.
Thank you so much. Thank you so much, Mwalimu. Yeah, so just a quick announcement. So tomorrow we meet same time to kind of go what was covered. For those who have time, I suggest you go through examples 29 and 30. You can check out the recording, go over that as you prepare. Also, I believe question 31 was homework. You can try to do that on your own. And then I know most of you guys took part in the ZK snack training by PhD. So they've asked us to fill a questionnaire